Okay, in this video we're going to talk about Unit 10, Objective 3, Volume of Known Cross-Sections. So this is going to be similar to our last objective where we had a region in the XY plane that was formed by the intersection of two curves, but instead of rotating that area around an axis to form a solid, we're going to use that area, that region, as a base for a solid, and we're going to build up from that base using known cross-sections. This does, just like the last one, have a formula to this that we need to know. So our volume of known cross-section is going to be a lot easier to remember, but sometimes it can get a little sloppy. So we're still going to integrate from A to B, but this time it's just going to be of A dx, where A is the area formula for the cross section. So some of our cross sections that we might get are going to be squares, rectangles, right triangles or equilateral triangles, and semicircles. Those are the ones that show up most frequently. So those area formulas you need to know. How we're going to use this is we know we're going to have that top minus bottom or right minus left that we have found we are finding the area of the region. How this is going to work is that top minus bottom will be part of our area formula. So if we're thinking about squares, that top minus bottom is going to be one of the sides of a square. If we're talking about a rectangle, that top minus bottom could either be the base or the height, and they'll kind of make sure you know on the question. If we're talking about right triangles, that's generally going to be the base or the height again. If it's an equilateral triangle, it's going to be the base, and if it's a semicircle, it's going to be a diameter of the cross section. So, looking at a question, what these might look like would be something like this. Let R be the region in the first quadrant bound by 1/2 x minus 1 and 1/2 x plus 1. Region R is the base of a solid whose cross sections perpendicular to the x-axis are squares. Find the volume of the solid. So what we're going to want to do is first let's kind of look at a picture of what's going on here. So 1/2 x plus 1 and 1/2 x minus 1. If we graph these, we're going to get this right here. So they're going to intersect at 2. Oh, there is a typo. I apologize. This should be negative 1/2 x plus 1. So now our graph is going to be correct, and they're going to intersect at 2. So region R is this region right here. So that's going to be the base of our solid. Now if we keep reading, it says the cross sections are perpendicular to the x-axis. So that tells us that we want the cross sections to look like that. So when we do that, we know now we have a top minus bottom situation, so we are going to want to integrate with respect to x. This is the type of problem where you're more than likely going to have to integrate with respect to y, and we'll know when we have to integrate with respect to y because they'll say our cross sections are perpendicular to the y-axis. So we have our top minus bottom there. We know from the question that we are dealing with squares, so we know A is equal to side squared. Now we just said that that side is going to be the top minus bottom. So the top function in this case is negative 1/2 x plus 1, and the bottom function is going to be 1/2 x minus 1. So you can simplify that if you want. So let's go ahead and simplify that. So s is going to be negative 1/2 minus 1/2 is going to be negative x. 1 minus negative 1, so plus 2. Negative x plus 2 is going to be our side. So our integral to find our volume is going to be the integral from 0 to 2, because just like when we were building our volume, we're going to want to build them going this way. So since we're building this way, we're going to stack everything up from the x value 0 to the x value 2. So our integral is going to be from 0 to 2. Our area formula is s squared. But we now know that s is going to be negative x plus 2 quantity squared dx. So that's how we're going to set these things up. I'll leave you to finish that problem for yourself. If you want to see what this looks like, it's kind of hard to see. We can look at this picture here. So it's the same function that we just had. You can see in the left side, it looks like the graph we made. You can see the triangle area R, and then the top minus bottom is that red little rectangle. And off to the right, you can see in 3 dimensions what has happened. So we can move this rectangle left and right, and you'll see that as we go to the left, the square, as we go to the left, going from top and bottom is going to have the same as the height sticking up from the top. So as the top minus bottom gets smaller, the height of this thing gets smaller until they're touching and there's not really anything left there. Now we can generate the solid so you can kind of see what it looks like. So we'd have that first big square, then another one that's a little bit smaller because the top minus bottom distance is getting smaller, and we can fill that all the way in, and that is going to be the volume that we just found, the volume of that figure. Now we can also look at this and see what rectangles would look like. That's going to make me come up with an equation, so we're not going to look at that one. We can look at isosceles right triangles. We can look at semicircles. So that's what this one would look like, a bunch of semicircles. But the big thing that we need to know is the volume of known cross-section is going to be the integral from a to b of a of x, where a is your area formula for the cross-section. So we'll call it quits on this video, and we'll see you in the next one.